Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. We are in chapter 13, part 1. All right, so last time we were talking about using the LEAPS package, and we built our models and compared them using the R-squared criterion. Now we're going to do the same thing, but instead we're going to use the adjusted R-squared criterion. So in the column here, it says R-squared adjusted, because now we're looking at penalizing the model for the number of predictors that we put in. So just as a reminder, these are all the models with one predictor in the model, with 2 predictors, with 3 predictors, and with 4 predictors. So I'm building all the possible models where, remember that the Y variable was crime, X1 was age, X2 is college, X3 is income, and X4 is sex. All right, so essentially we look through the R-squared adjusted values and we look for the highest values, and we see 2 possible models, and this is the model with age, income, and sex as our X variables. And this is the one with age, income, college, and sex in the model. So what we notice here is that we would end up choosing the model with these 3 predictors. The R-squared adjusted values are very close, 0.825 and 0.820. But remember also that age and college had pretty high correlation above 0.9. So you'd probably end up choosing that 3rd model. All right, so another criterion that we could use is called the CP criterion. And when we look at this CP criterion, the way we calculate it is by taking the SSE of that particular model and then dividing by the S epsilon squared. And what we can do is calculate the CP value. And overall, you're wanting to choose the model where CP is approximately equal to P. So this is just another way to choose between models. And so right here in the LEAPS package for the criterion, using this function here, I use the LEAPS function, and now I'm putting in method equals CP. And by doing that, I can look and see which values of CP are very close to P. So when we do this, note CP will always equal P for the model with all the variables in it. So 5 equals 5. We have 4 predictors plus the intercept. So those equal each other. But then we also notice that the CP criterion is giving us similar results as the adjusted R-squared criterion. So either of these models would be appropriate. So we're going to use the model with crime regressed on age, income, and sex as our final model. Essentially, you can use these different criteria as a guide. So it's not a hard and fast rule. You can use all this information to decide on your final model, but we have that, we have K predictors, right? K equals 3. That means that P equals 4. And the CP value in this case was 3.02. So these are very close to one another. So this would be an appropriate choice of model. So crime regressed on age, income, and sex. Okay, so essentially up till this point, we've been using best subsets, which allows you to build all possible models and then choose the model based on a specified best criteria. We're going to talk about 3 other model selection techniques. The first is backward elimination. So in backward elimination, you're going to fit all your variables. You're going to say that y follows, let's use our case where we had 4 variables, x2 plus x3 plus x4. In backward elimination, you're going to say, given all these variables in the model, should I drop any of the variables? And essentially, you keep on dropping variables until all variables in the model are significant. All right. In forward selection, you fit a model with just the intercept, and then you ask, should I add any variables? And you add one variable at a time. Until all your variables in the model are significant. All right. Now, as we know, once one variable is in the model, that could affect the significance of another variable. And so one other choice would be to do stepwise selection. And in stepwise selection, you're going to start, if you're doing stepwise forward selection, you would say, okay, I'm going to add variables in the model. But now that I have multiple variables in the model, I'm going to go back and check and see if any should be dropped out. And then I should see, are any of them significant? So you get to add and drop variables until you get your final model. So for stepwise forward, you're going to say, okay, here's my regression with just an intercept in the model. You're going to add the most significant variable. You're going to check. Should any variables be dropped? Then you're going to check. Should any variables be added? And essentially from here, you're going to just go back and forth until all your variables are significant. All right, so what we could do for our code is we can make a base model. So notice the base model only has an intercept. The full model has all the predictors in the model. To do backward selection, we're going to use the function called step. We're going to feed in the full model. We're going to say direction equals backwards, trace equals false. If you want to see all of the steps, you could change the trace equal to true. And then that will show you every step that it's being tested. All right, if you want to do forward selection, okay, so for forward selection, we're still going to use the step function, but now we're going to fill in the base because we're going to start with just an intercept in our model. And we have to tell it the scope. The upper is going to be set to full. The lower is going to be set to our base model. The direction is forward and trace equals false. Once again, you can choose to do trace equals true if you want to see how it steps through and selects the models. For the stepwise regression, we're going to start at the base, the scope. The upper limit is the full model. The lower limit is the base model. Direction equals both tells it that we're stepping both forward and backwards through the space. Trace equals false. Once again, you can choose to do trace equals true. And that will be able to get you the R code for your backward elimination, your forward selection, or your stepwise model. So I hope you learned something today, and I will see you next time.